Hello everyone, I'm Nil Sezgin. I'm working as a researcher at Siemens. I will be sharing our research on LLM-powered API testing framework based on structural similarity analysis. Today, we will explore a new approach to automating API test cases. Testing API endpoints is critical but repetitive bottleneck. Traditional rule-based generation from open API specs is inefficient and lacks human-like understanding. While LLMs offer immense automation potential, their lack of transparency raises reliability concerns. Our motivation is to bridge this gap, developing a framework that leverages LLMs to automate test generation while strictly ensuring structural validity and functional correctness. Current studies heavily focus on syntax and coverage, lacking quantitative evaluation of how well LM-generated requests structurally match API specifications. And to address this gap, we offer three key contributions. First, an automated framework using LMs to generate structurally correct API tests from open API specs. Second, a quantitative evaluation method using Jacquard-based structural similarity analysis. And third, experimental validation across different domains to prove its real-world effectiveness. Recent studies have effectively applied LLMs to different testing domains, including Java and JavaScript unit test generation, or video game test automation and mutation bug detection, but these previous tools primarily focus on coverage refinement and executable correctness. Our research fundamentally differs because it directly incorporates structural similarity analysis as a quantitative validation mechanism. By providing schema level measurements of structural fidelity, we move beyond simple execution success to ensure the generated requests strictly align with the formal API specifications. Our methodology follows a four-step approach. First, we extract API endpoints, methods, and parameters directly from the Open API specification. Next, during generation, we handle data pre-processing and create test cases using large language models driven by prompt engineering. And in the third step, validation, we execute these generated requests on real APIs to track errors and confirm functionality. And finally, in the analysis phase, we compare the generated structures against the expected ones. What makes this evaluation comprehensive is that it goes beyond simple execution success rates. By applying the Jacquard similarity coefficient, we quantitatively measure the similarity between field sets, giving us a precise metric for structural correctness. For our data preparation, we employed the complete OpenAPI specification for our Internet of Drones platform, which contains over 40 endpoints for critical operations such as telemetry and task delegation. We developed an automated extraction procedure to obtain the overall API documentation from JSON files, capturing endpoint definitions, schemas, and sample request bodies. Before test execution, this data underwent extensive pre-processing. We normalized the data, classified APIs based on structural attributes, and implemented quality assurance to avoid incorrect examples. And finally, our prompt engineering utilized an instructional framework to guide the LLM. By providing schema information with structural constraints and contextual interaction patterns, we iteratively refine the prompts to mitigate common pitfalls. Core of our structural validation is Jacquard similarity coefficient, which measures the similarity between field sets of reference and generated API requests by considering the intersection and union of field names. To handle complex structures, hierarchical fields in nested schemas are flattened using dot notation prior to comparison to ensure structural consistency. This evaluation allows us to measure the level of replication of the request structure by LLM, facilitating correlation analysis and failure differentiation. A higher Jacquard score indicates stronger structural alignment with the API specification. And in our score interpretation, a range of zero point 0.8 to 1.0 signifies excellent alignment, whereas scores from zero point 0 to zero point 0.4 represent poor alignment. Our experimental setup was designed to evaluate the LLM's effectiveness in generating valid test data across diverse API structures. To ensure coverage, we targeted 24 unique endpoints encompassing over 40 total operations. By generating 100 requests per endpoint, we compiled a robust dataset of 2,400 total requests, providing high statistical significance for our study. Our experimental procedure followed three clear steps. First, validating the generated test data with actual APIs, meticulously monitoring all request response cycles, and measuring the structural alignment using Jacquard index on a scale of 0 to 1. We categorized the execution outcomes based on HTTP responses, differentiating successful uh, executions from specific failures such as parameter validation errors, endpoint availability, method compatibility, and some technical infrastructure issues. We achieved a highly encouraging overall success rate of 84%. Out of the 2,400 test requests generated, 2016 successfully returned valid HTTP responses. This key finding confirms the LLM's strong understanding of API endpoint specifications and parameter structures, proving its viability for automating significant portions of API testing with minimal human intervention. For the remaining 16% of requests, which equates to 384 failures, we conducted a detailed breakdown. The majority of these were parameter validation errors at 6.1%, involving improper formats or constraints violations resulting HTTP 400 responses. Technical errors such as network or server issues accounted for 5.7%, and endpoint validation errors for non-existing endpoints and method issues with inappropriate HTTP methods made up the remaining minor fractions at 2.2% and 1.9% respectively. We achieved a mean Jaccard score of 0.827, which is significantly higher than the typical zero point 0.6 to zero point 0.7 range seen in other test generation systems. This indicates a very high structural consistency between the LLM generated requests and the formal API specifications. When we examine performance by complexity, the model maintains strong fidelity across the board, scoring 0.894 on simple architectures and a solid 0.756 even on complex ones. Looking at the score distribution, our key findings are striking. 89.4% of all generated requests achieved a score above zero point 0.7, representing good to excellent alignment, with 71.8% scoring above the zero point 0.8 mark, and only 10.6% fell below zero point 0.7, typically due to LLM producing creative but non compliant parameters. These metrics clearly demonstrate the LLM's profound understanding of API structures. Our structural similarity guided framework successfully integrates OpenAPI extraction, prompt-based generation, execution validation, and Jacquard evaluation. Validating 2,400 test cases yielded an 84% success rate and a 0.827 mean Jacquard score, providing the LLM's effectiveness. While we recognize limitations such as prompt dependency, gaps in semantic validation, and scalability concerns, these pave the way for our future work. Moving forward, we plan to implement feedback driven prompt refinement, reinforcement learning, and semantic metrics, integrating this framework into CI CD pipelines for large scale industrial applications. Thank you very much for your time and attention today. I would be happy to answer any questions you might have or discuss these findings in more detail. If you would like to reach out, my contact information is on the screen.